My name is Eva Zay. Dan Weeks and I both work on the Netflix Big Data Platform team, and we are very happy to be here today to talk about how we run Presto and Spark on the Netflix Big Data Platform. So in this session, we're going to talk about our big data scale, the architecture that we use to achieve the scale that we need. For Presto and Spark, we're going to cover the expanding use cases that we have, the performance that we see, the contributions that we make to achieve some of the performance gain that we get, how we deploy on EMR, and also how we integrate with the Netflix infrastructure. So at Netflix, product decision is largely data-informed and data-driven, and we use data to find the most optimal solution for any product idea that we have. And at Netflix, the big data platform is leveraged across the whole company for doing analytics and ETL needs. And I'm going to go through 3 examples that we use for the big data platform for. So this is a screenshot of our Ignite application. It is an A/B test analytics application that we use. Our product manager would use this application to interactively look at how their test case is performing. At Netflix, at any given point in time, we could be running hundreds of test cases at the same time. So in this screenshot, you see that they would look at retention and streaming hours across different test cells, across different regions and different devices. The data that power this application is generated by ETL processes running on the big data platform. We really care about user streaming experience, so we also publish a monthly dashboard that shows the average user streaming speed across different ISPs, across different countries. So in case you're wondering why your streaming doesn't work so well, you can take a look at this dashboard also. So we also use the big data platform to train data model for our recommendation engine and also help build the search index for our service. So these are just 3 examples that I picked, and there are many more use cases that we use the big data platform for at Netflix. So on to our scale. Currently, we are one of the top 3 biggest service running at Netflix on AWS. The biggest is Atlas, which is our telemetry system. The second biggest is Cassandra. They run over 200 data rings across all the regions that we support and that we run on. And Cassandra is our online data store. And we are the third. And the scale that we need comes from our business. We currently have over 65 million members in over 50 countries, supporting over 1,000 devices, serving 10 billion hours per quarter, accounting for over 37% of internet traffic during peak hours. With all that business needs, it translates into this big data scale that we have. We currently have over 25 petabytes of data on S3, and S3 is our data warehouse storage layer. And on a daily basis, we run ETL and analytics jobs that read around 10% of this data, process them. And in terms of data size, we spit back out or generate back out 10% of the data that we read and put it back onto S3. So that gives you an idea of how active or the data funnel, how it looks like in our data warehouse. And on a daily basis, we get 550 billion events from our service. And we have around 350 active users at Netflix using our big data platform in the past 4 weeks. So we need to continue to scale our platform because we want to be in 200 countries by the end of next year. So let's move on to talk about the architecture that we built to achieve the scale that we need. So first, let's take a look at where the data comes from. There are 2 main data pipelines. The first one is the event pipeline. An example of an event would be like you click play on a device or you search for a movie on our website. 550 billion events go into the Kafka data pipeline and then go into Ursula. Ursula is a distributed system that we built that actually merge each Kafka topic at the end of the hour. And each Kafka topic would present as a Hive table in our data warehouse. And we also, for certain Kafka topic or Hive table, we would pick out key value pair to promote them into top column in Hive. And then Ursula is going to write the data onto S3 and write the metadata onto Hive. One point to note is we are in the middle of transitioning to Kafka because it has at least one semantics. It's more reliable and durable, and also that's largely where the industry is going for data pipeline in the open source world. For the dimension pipeline, dimension data is something like user subscription data. We have an eggless pipeline that we build that we do daily extraction from our online data store, Cassandra, into our data warehouse for the dimension data. And then if you imagine yourself looking to the right side of the S3 bucket, that's the layer architecture diagram of our big data platform. On the lowest layers of storage, we use S3 as our data warehouse storage. Our data warehouse is largely in Parquet file format. On top, we provide a number of big data processing tools for our users to use, and I'm going to go over in more details in the next slide. There are two key services on top that we built. One is Genie. Genie is a federated execution engine that exposes an API for the users to specify a specific big data command or SLA and priority, so that Genie is going to can issue the job in one of the clusters in the compute layer. And Genie itself is actually open source on Netflix OSS, and we are also aware of a couple of companies that are using Genie. One advantage of Genie is also that you could actually swap out cluster in the back without impacting the user, and that's why we could do red-black pushes of our cluster when we need to do cluster upgrade. Metacats is a federated metadata service that proxy metadata requests back to the original data sources that we have, like Hive, Teradata, Redshift, and RDS. And it provides an integrated API layer for all the tools to access metadata, and it also provides an opportunity for us to add additional metadata context, like data category, TTL, retention, data ownership that is meaningful for us to track in the big data platform team. And we will open source Metacat in the near future on Netflix OSS as well. On the tools layer, we provide a whole set of tools for our users to use so that they could be more self-serve, more productive, and the data platform team can scale a lot better. I'm not going to go over all of them, and I just want to point out that both Lipstick and Inviso are actually open source on Netflix OSS as well. So if you're interested, you could take a look. Then on top of the tools layer, we built an integrated API layer so that layer is actually a Python library that allows integrated access to all the tools and services. We use that API from our external scheduler to schedule jobs in our system. And we also have a one-stop shop big data portal built on top of that API that allow our users to do interactive querying or access to our tools and service. So, zooming into the compute layer, we provide 5 different big data processing engines for our users to use, or tools for our users to use. Hive is for analytics, Pick is for ETL, Presto is for interactive data exploration plus more, which I'm going to talk about later. Druid is the backend for our A/B test analytics application. If you may remember, a few slides ago I showed Ignite. That's backed by Druid. It serves as an in-memory cache so that users can do interactive slice and dice. We also included Spark in our platform this year. It's going to expand the use case of our platform by allowing users to more efficiently do interactive ML algorithm, real-time analytics, and more. So in this session, I'm going to focus on talking about Presto, and Dan is going to focus on talking about Spark. But before we get on to Presto, I just want to point out the key underpinning of our big data architecture, which is we choose S3 as our data warehouse storage layer. Amazon S3 is where we put our data, and it's the single source of truth. And the reason why is definitely it would be likely more durable and reliable than your HDFS cluster. It allows us to separate storage from compute. Basically, it allows us to run different clusters on the same set of data on S3. And also, it allows us to easily do red-back pushes. For example, when we need to upgrade the software on a cluster, we could spin up a new cluster, start routing new jobs to it from Genie, wait for the old cluster to finish its job, and then deprecate the old cluster. And it's a common belief and questions about the performance of S3. If you reuse S3 as a storage layer, it's going to be slow. And we just want to clarify a little bit before you ask that Actually, S3, it has a much bigger fleet than your cluster, so it could sustain a lot bigger throughput than you could. You could offload some of the work onto S3. In terms of a purely benchmarking environment, we do see that if we use S3, there is some read performance impact because it's definitely going to have more latencies. But in our use cases, our jobs are very CPU bound, and it's very large, complex job that has multi-stages, and the impact is only going to be at the read stage at the beginning and the write stage at the end. So it's very insignificant. The benefits definitely outweighs the cost. Same goes for write, and actually sometimes we see that writing to S3 is a little faster because S3 is eventually consistent. So hopefully that helps explain that. And now we can talk about Presto. Presto is an open source distributed SQL engine, open source by Facebook on GitHub. It is an interactive analytic engine. It is very different than other traditional big data processing engine in the sense that data stream through the Presto workers, never touch disk, and all stay in memory. And hence, it can achieve the interactiveness that it has. And it also scales up to petabyte scale in our use case, as well as Facebook use case right before they open source it. So why do we love Presto? It just simply fit into our architecture very well. It's integrated with Hive Metastore, and it also integrated with Amazon S3. When we first started using Presto, we spent about a month to collaborate with a Facebook engineer to work on the S3 file system in Presto. And after a month, we have an initial version of the S3 file system working. So that's pretty easy for us. And it works at petabyte scale. It is an ANSI SQL syntax, so your analysts or engineers or data scientists, they usually know about ANSI SQL, and it's open source, so we could enhance it for our own use case. It's written in Java, and it's really fast. So how fast? So we benchmark Presto and Hive again. Presto is when we do the benchmark, we're using Presto 1.14, Hive 1.0, running on MapReduce. And the key takeaway of this chart is that Presto finished in seconds, Hive finished in minutes. On the first two queries, you can see that if you are running queries that are more complex, you will likely achieve more savings in Presto because it could avoid a lot of it could avoid more disk I/O because if it's complex queries in Hive, you are likely to have more stages and have more disk I/O. The last query showed that needle in a haystack scenario, Prestos run really fast. And it's actually super fast for big data analytic queries. And I'm going to cover why that's so fast, and we did some contributions to make that happen. So at Netflix, we run around 3,500 Presto queries a day, out of which 60% finish within 5 seconds and over 90% finish within a minute. And that's extremely fast in terms of querying big data, and that's why our users love it so much. It tremendously improves their productivity. So when we first started using Presto, it was for interactive data exploration and experimentation, but because Presto runs so well, we start to expand using Presto in more use cases. There are users who use it for data validation. If they suspect their ETL job has probably some problem in the data, they would use Presto to do data validation to make sure the data that they generate from the ETL process is within their range of expectation. We also use Presto as a backend for that A/B test analytic application, Ignite, that I showed a few slides ago. I mentioned that we use Druid for interactive slice and dice, but there's one thing that Druid cannot do is the distinct count query. So in that case, the Ignite application actually point to a Presto cluster and to do the interactive and do the distinct count queries for the interactiveness of Presto so that the application can still have the interactiveness that we need for the product manager to use. And in terms of reporting, we use Tableau and MicroStrategy, going through Hive server to Hive for our big data reporting needs. But we definitely want to move to Presto because it's so much faster. And we recently implemented the Web Connector interface in Tableau to connect to Presto. We're testing that out, but we are also aware that Teradata is going to come out with an enterprise ODBC and JDBC driver for Presto, and we're excited about it, and we'll certainly test it out when it comes out. And because Presto runs so well, our users keep pushing us to actually make Presto available for ETL. But Presto is not designed for ETL. As I mentioned earlier, all data that go through Presto never touch disk, and it stays in memory. So in other words, if you run a query on a large set of data, you could fail the query or even push over the cluster. It's possible. So it's not really designed for ETL. But what we're exploring with our users is maybe there is an happy medium where they could run scheduled job on Presto, potentially on a dedicated cluster, that they could actually sacrifice some reliability for the gain of having the query run fast most of the time if they could live with having it fail occasionally. So we'll see how that goes and see how that use case develops. So on to talking about our deployment, we're currently running version 1.14 with some patches. All of these patches are public, so you can run what we run, except for one patch, and I'll talk about why that is not public yet. We deploy Presto on top of Amazon EMR using a bootstrap action. We actually run two separate sets of cluster for Presto and for Hadoop workload, and it's because Presto needs a different kind of instance. Presto needs a lot of memory versus the Hadoop cluster needs a lot of disk for temporary storage. For the Presto cluster, we're not using any of the Hadoop service. We're not running on HDFS. And we are using EMR primarily for resizing the cluster and node replacement. We currently have two production clusters running. One is for ad hoc querying that I mentioned. One is also for the application cluster, which is the backend cluster for Ignite, the A/B test analytic application. The reason why we need two production clusters is because of resource isolation. In Presto, they manage resource by limiting the number of queries that users can run. And they also can specify a limit on the memory that a query can have, but it doesn't cover all the operators yet, meaning that a single query can still take over the cluster and potentially push it over. And in that case, what we did is to separate the two clusters so that the interactive Ignite application can have a dedicated cluster for running the queries that it needs. One thing also interesting is that for the Ignite application cluster, we're using dynamic sizing by querying the Netflix Spinnaker API. Netflix Spinnaker is the continuous delivery platform that we use, and it provides an API that allows us to see what are the unused but reserved instances that we have across all the accounts, all the region, all the different zones, and all the instance types. So basically, we can find out how many instances that we could borrow. And it works really well for this application cluster because when it's the busiest during the business hours, when a product manager is working, actually it's the trough time of our site traffic. So actually we could leverage the unused capacity for our application cluster. So this chart shows that over the course of 4 days, how we actually size up and down our application clusters. And you see that we are leveraging R3 XL and 4L. It's just happened that over those 4 days, we can't find any available R3 2XL. So how we integrate it with the Netflix infrastructure. So this diagram here is showing that there is a Presto cluster with one coordinator and many Presto workers. Each of these nodes is running the Presto process. And there is also a sidecar process that we inject into the cluster via our bootstrap action. Basically, the sidecar process on the coordinator is sending the query information and the user information down to Kafka, our data pipeline, and then we can do data lineage analysis downstream. And all of the nodes on the Presto clusters also send metrics that we care about and also send JMX metrics that's provided by Presto down to Atlas, which is our telemetry system. From the coordinator, we send metrics like user queries complete, failed. From the workers process, we send statistics, metrics like S3 read errors or number of concurrent S3 connection at this point in time. So then I'm going to spend the rest of the time that I have on the stage to talk about the contributions that we make and the performance gain that we achieve. So in the last year and a half that we use Presto, we make quite a few contributions back. We worked on the S3 file system. We optimized a couple of queries type that our users use. We added various functions for complex type like map, array, and structs to close the gap between what's available in Presto and what's available in Hive. This year, we'll spend a lot of time to optimize Parquet file format with Presto. Everything you see here is already available out there. The only thing that's not available is Vectorized Read, and I'll explain why. Everything else is available. The two items that are in asterisk are the one that is available as patches, not contributed back yet. I mean, not committed yet. So I'm going to spend the time to talk about Predicate Pushdown and Vectorized Read. And before I do that, let's take a look at Parquet file format and what it is. Parquet is a columnar file format. It is supported across the big data engines that we use. And because it's so neutrally supported across these engines, the performance gain that you are going to see that we have in Presto can arguably be implemented across these engines as well. So that's the advantage that we have picking a neutral file format. It works well on S3, and most of our data in our data warehouse is in Parquet file format. And as far as we know, we might be the biggest data warehouse on Parquet file format. And if you find another one, let me know. So basically, let's take a look at how Parquet file is organized. So Parquet file organized rows in rows group. Each row group represents a number of rows, and they're organized in column chunks. Each column chunk has multiple data pages, and if the cardinality of the value in that column chunk is below a certain threshold, it would have a dictionary page that contains all the unique values in that column chunk. Then in the footer, it will have the statistics and metadata for all the row groups and all the column chunks in each row group. When we talk about vectorized read, we're talking about how we optimize the read on the column chunk. When we're talking about predicate pushdown, we're talking about how we leverage the statistics in the column chunk metadata and the dictionary page to achieve data pruning for the performance gain we get. So for vectorized read, we basically implement a new Parquet API to read column chunk by batches instead of row by row. We implement the similar change in Presto to integrate with the new API. Because Presto is a vectorized execution engine, we actually, in a read-bound query, or in a read-only query in Presto, when we benchmark it, we see 2x performance gain for primitive data type, which is really good. And there's a lot of interest in the community to do that. Spark is thinking about using it because they are also thinking about to make it a vectorized engine. Hive is already a vectorized engine, so there is some activities in the community to actually implement this in Hive. For Drill, we actually collaborate with the Drill team to design the Parquet Vectorized Read API. So the reason why this patch in Presto is not available yet is because we're waiting for the Parquet JIRA to be committed. Once it's committed, we'll make it available, and we're talking about probably weeks, not months. For predicate pushdown, we're really excited about the performance gain we see. And it's best illustrated by an example. So let's say the predicate column is A/B test ID, and you're looking for value 10. So we first look at the statistics on the predicate column chunk for the value that you're looking for. If the value that you're looking for fall out of the column chunk statistics, we can completely read that row group in Parquet. But let's say the value that you're looking out for actually fall into the statistics of the column chunk stats. What you need to do is actually go to the row group and read the dictionary page and see if the value exists. If it doesn't, it can skip. If it does exist, it will end up reading all the data pages in that row group. So if you step back to think about it, it is the best case if you could actually cluster or sort or order the data by the predicate column. For example, if your predicate column is very evenly distributed across the whole file, the statistics range for each column chunk will be really wide. You will end up falling into the range when we do predicate pushdown most of the time, and then, which is not good, because then you end up needing to read the row group. And if the predicate column value actually appears many times have a lot of repetitions, again, that's not good if it's evenly distributed, because then you will find it in multiple dictionary and end up reading a lot more data pages than you need. So basically it works best if you cluster the data by the predicate column that you are choosing on most of the time, much like how we plan a Hive partitions. But in some cases, Hive partition doesn't work well because the predicate column that you are most likely select on has a lot of distinct value. The cardinality is very high. Then it doesn't make sense to create millions of Hive partitions and overload the metastore. So we're really excited about the result. I'm going to share that next. But what I want to point out is we are likely and thinking about implementing this predicate pushdown logic in Spark, Hive, and Pig as well, simply because it works so well. So let's look at a real use case and the performance we get. So we do analytics on Atlas data. Atlas collect over 1 billion of time series data from our service. Most common analytics use case we have on Atlas is they want a particular metric for a particular application for a particular time period, like this example. And we pick a day to look at how many distinct metrics we have. And that day that we picked, we saw 1.7 million. So it's very high cardinality, it's high selectivity. So what we did is we restaged the data so that it's clustered by the app name and the metrics. So we see 10x performance gain on the query running on the Presto cluster, which is very, very significant. We also observe that we have 170x improvement on CPU usage and also all the I/O metrics. So basically what it's saying, the cluster is actually much more free for doing other workload. So like I said, we are likely to implement it in other engine, but this patch is already committed in Presto, and so you could use it as well. So that's all I have for Presto. I just want to point out that we're going to have 2 tag blocks talking specifically how we use Parquet file format and also how we do the performance improvement of Presto on Spark file format. So stay tuned for that. And with that, I'm going to have Dan come up to talk about Spark.
Thank you. So this next section, we're going to be talking a little bit about the work that we've done to integrate Spark into our platform. And I have to point out that Spark is the newest addition to the platform, so it's in a very different state of integration than Presto was. So Presto, we're spending a lot of time working on optimization and building out new use cases and functionality, whereas Presto, we're trying to figure out how best to integrate it with the platform and make it play well with the other tools that we have. So for those of you who are not in the big data space, Spark is a general engine for doing distributed computation. And we have a lot of engines that do this kind of work, and Spark is a little bit different in the sense that it's not a domain-specific tool. So Hive, Pig are very domain-specific in that you're going to be doing analytics with them, you're going to be doing some sort of data transformation or ETL with those. Spark is built on top of a set of core libraries for executing any sort of data transformation. And then on top of that, you build domain-specific tools. But the nice thing about this is that they can all play together very well. So why do we want to use Spark? I mean, we've just described a very mature platform that we've been using to do big data processing for years. And we have Hive for ETL, we have Hive for analytics, we've got Pig for ETL. So what does this bring to the platform that wasn't there originally? And what we're actually seeing right now is a growing number of cases where people need either iterative use of data or they're going to be doing some sort of machine learning and they need to scale this out. Most of this kind of work right now is being done on single instances or somehow sharding across other clusters to achieve the same kind of result. So Spark provides this and is one of their, the core features of that particular platform. The other thing that we see is an increase in programmatic use cases. And what I mean by programmatic use cases is cases where we're actually either adding more logic to the actual job or we're doing something in addition to what would normally be done via Hive or Pig that is domain specific. And we've got ways that we kind of shoehorn these into those tools. With Pig, you can use load func, store func to do extra functionality, but it's not really idiomatic of Pig, and it doesn't make a whole lot of sense when you're looking at something and you've got these strange conventions to do this extra work. So one good example of that is what we call continuous processing. And what we do with continuous processing is we actually try and decouple what data you need to process from the actual execution. So rather than saying, oh, I need to process the last 8 hours of this table because that's where the new data is, and having to explicitly call those out, we use an external tool to keep track of that, and you have just kind of a high watermark where you can go and you can say, get me all the data that I haven't processed yet. And then at the end of these jobs, you might say, well, I want to do some sort of analytic across them to make sure that the data actually conforms to what I expect it to be. Doing this in Spark makes a lot of sense because it's very programmatic. You can build these things in with your job as well, where with the other tools, it's a little bit more difficult to do. So we're not the only team at Netflix that's actually using Spark. We have an image that is provided by another team using the same source repository that we use, so we collaborate on the actual building out of features and things like that, but they have a separate AMI that they can spin up for specific use cases, and this includes the entire Berkeley data analytics stack. And the important thing about this is it's really more for targeted use cases. If you're going to be doing streaming, or you have a machine learning job, or you have certain SLAs, you need to have a dedicated cluster for that. And that's what they use this for. However, in our case, we're actually deploying a little bit differently. And the reason that we do that is because we're more focused on the batch side of things, doing large-scale processing where you're not as concerned about the SLA, but you want the scale. And our focus there is also on resource utilization, making sure that we're actually getting good throughput and we're harnessing all of the power that all the power of the cluster all the time. So this means that we can actually do some interesting things by running it on top of Yarn. One is that we actually provide Spark as a service. So instead of having a standalone cluster, we actually provide Spark as something that is somewhat decoupled from the actual execution. We run this on top of Yarn in EMR. So EMR is just going to be providing the Hadoop cluster with Yarn running on top of it, and we're providing the actual application. And again, the focus is more batch analytics, but we do support the full stack capability, so you can do interactive, and we'll go into that a little bit, as well as any of the other tools that stand on top of the Spark core libraries. So one thing that we can do as far as providing Spark as a service is version support. And this is kind of an interesting concept and makes something that is typically very hard very easy. And that is doing upgrades or supporting multiple versions of the same product on the same cluster at the same time. So if you think about something like Hive, where you're tied with a specific version of the Metastore, there's a lot of work that goes into making sure that when you do an upgrade, everything upgrades seamlessly together and everybody's running at the same version. So with Spark, the way that we do this was we actually send the application with the execution to the cluster, and this allows us to separate those two concepts. So how this actually works is we have wrappers around the Spark shells. You can provide an argument for which version. We can do custom versions. And what it does is it talks to Genie. The script will talk to Genie. It'll get the information from Genie about where the application is in S3. So we just tar up a build of Spark, put it in an S3 location. And then it also, Genie contains the configuration information for all the clusters. So based on what other parameters you set, you can identify which cluster you want to run it on. It'll grab the configuration files, take these things, put them together, create a custom execution environment for you, and ship all of this to the cluster for execution. And this is very effective because we can basically have any number of versions of Spark running at the same time on the same cluster. Makes upgrading pretty much seamless. And this is particularly important for Spark because Spark is the most active Apache project right now. And so they're iterating very, very quickly, and we can't have all of our users have to go recheck their jobs every single time that we need to do a small patch or a push. They can stay on the version that's working for them, and then we can actually switch versions and test to make sure that they can actually upgrade seamlessly, and then only handle the cases where it doesn't work. So the next topic is actually about multi-tenancy. This is very important in order to get the scale and execute using the entire cluster. So just a little bit ago, we talked a little about separating compute from storage. And you might be saying, well, it doesn't make sense at this point. Why don't you just run a separate Spark cluster? You can do that at this point. It's what we do with Presto. And the reason is, if you look at this chart right here, this is actually one of our big clusters and all of the MapReduce jobs that are running on it. And I've highlighted the Spark jobs. And as you can see, Spark is not dominating the cluster by any means. People are still using it for exploratory use cases and just feeling out the capabilities and figuring out how they're going to build their workflows with Spark. The important thing here is that there's a trade-off between resource utilization and performance. If we stood up a separate Spark cluster, it would either have to be completely oversized in order to get the performance they want, or it's going to be so small to be resource efficient, and they're not going to get any performance out of it. So we really wanted to actually coexist with the other applications that are running on top of Yarn. And in order for this to work, one of the most important features is dynamic allocation. So this is something that was introduced into Spark in 1.2, and it's been iterated on many times. I believe 1.6 has probably the most robust implementation that'll be out sometime here in the future. But the point is that dynamic allocation allows us to harness the entire scale of the cluster, optimize for resource utilization, and the last point is most important, still provide interactive performance, which is one of the nice features about Spark is that you've got a cluster waiting to do computation, you're not going to be submitting jobs. And to understand this, you kind of need to understand the execution model of MapReduce and Spark. So if you look at the bottom, the traditional execution model is that a task and a container have a life cycle that are bound together. So one task will exist with one container. When the work is done, those get torn down, and somebody else will be able to reuse those resources. Spark on Yarn works a little bit differently in that you have persistence. So the containers are going to be allocated, and they're going to stay there through the entire life cycle of the job, and then tasks are kind of streamed through as the executors process them. What dynamic allocation does is it looks at how many tasks are pending for any sort of transform that's occurring at that time, and then will scale up and scale down based on how many resources it thinks it needs. So the way that we actually configure this is we configure just 3 executors when you launch a Spark job. So whether you're doing an interactive shell or you're doing a submit and forget type of execution, you get 3 initially. And what that allows you to do is any sort of quick operation, like a take 10 to just look at what your data looks like, figure out what you're going to join on, find the right columns, they'll execute very quickly because there are some containers just waiting to process those tasks. Whereas when you do processing for, let's say, an entire month, it's going to scale up based on how many tasks are generated from the split calculations and everything else. So it's not really important to know what the legend is on this, but it's a graph of one particular execution using dynamic allocation. And what you're looking at is that spike is really what Spark is considering it needs in order to process the resources as fast as possible. And the lower lines are more about what was actually allocated and deallocated during the execution. And the important thing here is that these are not perfect in a sense that you're not getting exactly what you want, exactly when you want. But overall, the execution is very good, and it means that we can share resources with other MapReduce applications and other things on the cluster effectively. So one other thing about Spark is that it allows you to cache data. So if you're doing iterative processing, interactive processing, and you've got a data set you can fit into memory, you just load it into memory. It doesn't have to go back to disk every time it wants to do some processing. Well, this works really well, except dynamic allocation originally was designed to remove executors from the cluster, containers from the cluster, when it realizes that there isn't any work to do. And this was kind of in contradiction to the caching idea, because what happens is you load a bunch of data into memory, and then it says, okay, I'm done processing all of this, and it takes them all away. So this was one of the first issues that we ran into with cached data. And the solution to this was adding a different timeout for containers that actually cache data. So we set this to 15 minutes, which means that people who are doing interactive work have enough time to work with it. But if they stop doing it, it's going to release all of those resources back to the pool so other jobs and other people can take advantage of them. Preemption. So preemption is a concept that's been in Hadoop for a long time now, but running Spark on top of Yarn shows you that there are some kind of differences between the philosophy of the platform. Spark had no concept of what preemption was originally. And so that meant that in a dynamic environment like ours, where you have different jobs with different weights, a new job comes in and it starts taking resources away from a Spark job. And what happens is Spark considers that failures, because all it's seeing is executors that are being killed. Now this is a problem because if it happens enough to the right tasks, then your Spark job fails. So this started happening, and we realized that this is a particular problem because it needs to understand not just how Spark works, but how Yarn works as well. So this was taken care of, and the solution was to make sure that they understand that preempted tasks can be retried and should be retried. This next section, I'm going to be talking about some of the work that, or issues that we've run into while reading, processing, and writing data. And some of this actually applies more to AWS, some of it is core Spark, and some of it is the way that Hadoop works in general. So the first is actually listing in S3. S3 definitely has additional latency in comparison to HDFS, and one of the major parts of any job, of course, is the setup where you go and you calculate splits and you do list operations. Now, we have a lot of metadata, and our metadata is so large that clients can't necessarily always hold it all in memory. We run into problems with projecting or pruning partitions. And with this many, one of the issues that you run into as well is how long it takes to get through all of those in order to list. And when this becomes a problem, then the clients will take hours before they can actually submit a job to the cluster. And that's time that we don't really want to waste on the client side. We want most of the computation to be done on the cluster. So in Hadoop, there's actually this concept of just parallelizing this. And because Spark actually reuses many of the same Hadoop classes, you'd think you'd be able to set these properties and get this parallelism. But you can't. And that's partially due to the way that Spark actually handles partitions. It actually keeps each one of them as a wrapped Hadoop RDD, and then they go through them in sequence. So if you set this property to do parallelized listing, all it's going to do is it's actually going to list each Hadoop RDD, or within each Hadoop RDD, but there's only one partition anyway, so you don't get any performance benefit. So there are a couple of JIRAs that address this, and there are really two issues associated with using listing with S3. The first one, as I mentioned, and the second one is that Hadoop does this second check to look for locality. And since we're using S3 as our data warehouse, we already know that it's not going to be data local. You're not going to be able to get your compute resources to where the data is. So why do this check? It adds an extra call to S3 for every single file that has to be listed. So the solution was actually to change this a little bit. So the change includes how Spark actually handles the set of partitions and to list them in parallel. And secondly, to use the Amazon S3 client directly to get the information about the files so that it doesn't do the second check like Hadoop does. And as you can see, the performance improvement is very significant. We're actually not talking about a whole lot of partitions here. I mean, 720 is pretty small. We regularly have jobs that are doing 10,000 partitions, even 100,000 partitions. And as you can see from the times associated with this, many of those would never be able to even kick off. So this is a particularly important improvement and is great for integration with S3. I believe the JIRAs for this are still outstanding, but they're being worked on and reviewed right now. The next is actually writing data to S3. When Hadoop was built, it was really tightly integrated with the HDFS file system. It makes a lot of assumptions about how that file system behaves in order to do its commit logic, specifically atomic renames. So that's how it kind of does its, choosing which task actually was successful. It moves it into the final location using an atomic rename. And as you may know, S3 doesn't really support this. A rename operation or a move operation is really just a copy and delete. And that's bad for a number of different reasons. One, because of the extra time that it takes. There's eventual consistency associated with it. And lastly, if you're using version buckets like we are, you get a second copy of all your data in S3, which you probably don't want to pay for. So the solution to this is actually to change the behavior of how output commits are done. And what we do is we actually change the logic so that it writes out to the local disk first for the temporary storage. And then when it actually does the commit operation, we do an upload to S3. And this can actually be pretty efficient because you can use multi-part upload for large files and other sorts of optimizations. And of course, this avoids all of the problems that we just discussed before. There's still issues with the eventual consistency, but they're different kind of issues. You don't have to worry about, the copy not being available on the following list operation. And the last thing, of course, is we add the additional functionality to write it to a new S3 prefix, so equivalently an HDFS path each time. We do this using the Hive metastore so that we can just postfix some sort of identifier to the end of the partition location to prevent any sort of update inconsistency that can happen on S3. Now, I mentioned a lot of issues that we ran into. That's actually just a subset of the things that we've been working on to integrate this into the platform. We've made a number of contributions to Spark, and a lot of those other issues, it's a combination of work that we've done, work that the community's done. As I said, it's a very active community, and so there's a lot of work going into making it work in the cloud as well as in the data center. So what are the next steps for Netflix? As I mentioned, this is very early on in the integration with our platform. We still need to do more work as far as metrics are concerned. With Hadoop, it's been around for a long time. We collect a lot of metrics. We understand how jobs are performing, and we can't really do the same thing right now with Spark, and we want to have that kind of insight into how these jobs are running. The next is data lineage. We have a lot of data, a lot of tables, and with as many people that are using the system, it's hard to know that if you're going to make a change to a data source, who's going to be impacted. Or if you're trying to find who's producing data, where they are and who's actually making that data available. So data lineage is something that we built into all the other tools in our stack, and we can answer these questions. But right now with Spark, it's a little bit of a black box, and we're working on that as well. And lastly, as Eva had mentioned before, the Parquet integration. We're a very big Parquet user, so we're interested in the performance improvements that she had discussed, and we want to add them to Spark and to all of the other engines as well. So there are some key takeaways from this talk. And the first, of course, is decoupling our compute from our storage. And this is why we use S3 for our data warehousing. There are a lot of other advantages to using S3, including the durability, the versioning, but separating the compute from storage actually makes a lot of things that are hard when you silo that, in a typical data center where you silo your data with your actual compute, very easy to do in the cloud. The next is that we use EMR a little bit differently than most people do. We use it not just as a provider of MapReduce, but as a cluster manager. So with Presto, we're not actually using the Hadoop distribution at all, and we just take advantage of the fact that they're monitoring the cluster, removing any sort of problematic nodes, and then the intelligent grow shrink capability that they've recently put into the cluster management. Spark, we run a little bit differently. We actually use it as a co-tenant on Yarn. And so in this case, we're actually using the full resources of at least the Hadoop distribution that they provide. And lastly, we're very committed to doing open source projects, to contributing our work back to the community, because everybody can take advantage of these resources, and we take advantage of the contributions that other companies are making. And if you're interested, you can always take a look at either the patches that we've provided, or you can take a look at the JIRAs that I listed earlier. So what's next? We mentioned that we do some graceful shrink or some resizing of clusters based on utilization and other things. We actually want to expand these use cases. We want to do this more with our larger Hadoop clusters. We want to integrate it with other tools in our ecosystem like Atlas and Spinnaker, so that we both know what the load is on the cluster, what's available, and do more dynamic reshaping of the clusters to take advantage of the resources that we do have. And the last thing is we want to expand use cases, figure out how to harness these tools better to solve problems for people that are using the platform, integrate Spark, and explore Spark as an option for ETL. So with that, thank you very much, and we can take a few questions.